Why can't our thinking be in one particular domain? Why do we need this another domain called frequency domain? So what's the use of this Fourier representation? So how can we see the signal visually? What exactly you need to know about Fourier representation and what is the application of Fourier representation, we are going to see today. Okay, don't worry. I know mathematics terms you are good, but you have to understand why do you read that. So what is the major application? Where do you actually, in real life, where do you apply that? Okay, so signals and system. So this is a good subject. Why? You can see the signals visually. Okay, that is the beauty of the subject. You use mathematically to write x of t greater than t or x of t less than 1 or something, but in signals you can plot it and you can visualize it and you'll get a better understanding. So whatever the mathematical tools are there, we are going to exploit it for the better understanding and application. Okay, so having said on that note, let me begin today's chapter on Fourier representation of signal. So you have a signal x of t, you can represent in terms of Fourier or Z or Laplace, but here we will see the Fourier representation. So Fourier representation means Fourier series or Fourier transform. Okay, where do we use this Fourier series and where do we use this Fourier transform? Everything we will see. Okay, so coming to the chapter, so actually this module 3 and module 4, they are like almost same. Okay, module 3 is about Fourier series and module 4 about Fourier transform, but in real life application, whatever you apply is Fourier transform. Fourier series, why do you learn? For the development of Fourier transform, it comes from Fourier series. Okay, so what are the things you learn in this Fourier representation of the signal? First will be introduction, then Fourier representation for 4 signal classes, then discrete time Fourier series representation, then continuous time Fourier series representation. Okay, okay, so now the first question to you is, you have to ask yourself, why this frequency domain? Why not only time domain? Okay, that is the first question. So why is the question, and the answer is simple. So consider a signal here. Okay, so you have a signal which has 3 components. Okay, 3 frequency components. One I have represented in blue, one I have represented in green, and another in orange. Okay, so if you view in time domain, what happens is your point of view is from this particular man's point of view. So you can see his bald head, right? So you're sitting from there, you can see. Okay, so now if you see here, this blue line overlaps, or you can't differentiate easily the 3 frequency components if you see in time domain. But if you see in this point of view, the second man's, so half face you can see, right? You can see the 3 different frequency component easily. So in order to get a better exact picture of that particular signal, okay, we are going to use this frequency domain. Okay, so this is a, you know, like sublayered like type of understanding. So practically, okay, what type of instrument you use for the analysis? So if you go to the electrical lab, you have something called as oscilloscope. So I don't know whether you have used oscilloscope, you know, due to this COVID situation, lab is not there. I don't know whether you have used in the previous sems or not. So if you have used oscilloscope, you can see the time domain signal practically. So what is this frequency domain signal? What is the instrument we can see the frequency domain or the frequency component in that particular signal? We use an instrument called as spectrum analyzer. So this spectrum analyzer will be helpful for you to analyzing the frequency component in a particular signal. For example, there is a real-time signals, there will be many frequency in it. For example, when I speak, there will be like 10 hertz component, or like some 25 kilohertz, or like between 10 kilohertz to 25 kilohertz, there will be many frequency component. So in order to analyze that, if I want to get this component, so there will be like peak like structure if you see this spectrum analyzer. So that components you can observe visually using spectrum analyzer. So you can see physically how this frequency domain look like and how time domain signals look like. So you cannot complain whether I can see that time domain signal or whether I cannot see that time domain signal. So that is the beauty of the signals. So you can visualize that one. Okay. So now we'll go to the basics. Okay. What is this frequency exactly mean? Okay. You may say that frequency is equal to inverse of time. That's also correct. Frequency is equal to 1 by time. I completely agree. But what I can say actually is how fast a signal is changing. Okay. Frequency means how fast a signal is changing. So consider this green line. Okay. Whether this signal is changing, only this green line, straight line? No. So it has a frequency of 0. Then let us consider this small change, okay, which is sinusoidal. So the frequency is medium here, okay. Then consider the last thing which I have plotted, okay. So you can see I have plotted closely to each other. That means the frequency content is more, okay. So it's like compression and expansion, frequency high and frequency is less, okay. So that's what you can see visually in terms of frequency, okay. So now let me explain to you why this frequency domain or frequency domain, why we need to learn, or what is the need for us this to understand this frequency domain signal, okay. So this is me left side who is seeing this guy. So consider this guy Imran Hashmi singing, and there is, let the signal be x of t, whatever sound wave he produces, and background music, any of your class guys, Akash is giving this piano, okay, and guitar is played by Ananya, okay. So we have x1 of t who is singing Imran Hashmi or something like that, and x2 of t piano sound, and x3 of t is our guitar sound, okay. So how can you represent this signal y of t? A1. So A1 is your amplitude factor, how much gain you increase or decrease, into x1 of t, plus A2, how much gain in that piano you have to increase or decrease. There will be a settings, okay. If you observe practically, whenever you give to a audio amplifier, there will be this one, whether before you give to your sound box, there will be amplifier section. So you increase or decrease the gain there, okay. Usually in your marriage functions, you call them as DJs. Actually they are nothing, they are not DJs, they only increase or decrease the sound, okay, or only they play the sound. You can't call them as DJs. DJs are separate, okay. So A3, you can also increase or decrease the signal. So now consider condition, a person is singing, and there is a lot of music components coming here. So your y of t is equal to A1 into x1 of t plus A2 into x2 of t and A3 x3 of t. So now let us consider the condition where there is a baby, he or she is crying. So there is a baby here whose noise, we can take that baby's whatever it's crying as noise, okay. So that one should be eliminated from our system. So what will be the output for our system? Y of t is equal to A1 into x1 of t plus xn of t. So xn is your baby's voice signal, okay. So the baby is crying. So Imran Hashmi is singing, or any singer, sorry, I am not good with it, okay. Any other singer is singing. So what do you want at the final end? You want only the person who sings. You should not have any other noise. Like, I have taken your baby noise, let it be any noise, okay. So you want to eliminate this. But if you want to eliminate this, how can you eliminate using a time domain signal? Like, if you do something to this equation, how can you eliminate it? So if I make this A1 this particular section A1 as 0, my okay, this x1 and x2 will become 0, but my whole signal a2 x2 of t and x3 of t will be there, but my whole signal x1 of t also will become 0. Whatever Imran Hashmi or another singer is singing, it should not be lost, it should be there, but only the baby's voice should be eliminated. So now comes your frequency domain analysis into picture. Okay, so if you consider this equation, x1 of t is your singer's noise, xn of t is your noise from the baby which you need, then x2 is of piano and x3 of some guitar. So now what we want, this xn should be 0. Okay, so I will take them frequency representation. So if I take the frequency domain representation, this green color represents the magnitude of the signal of the singer, and this noise is given by the baby of the red. So this red color, whatever you can see, it's a noise from the baby. So now we will use a simple filter. So I will multiply this signal with a magnitude of 1 and its width only of that of the singer. Okay, so I want to extract only that component where the singer is singing, and I want to eliminate this whatever this baby is crying. So I will multiply these two. So what happens, if you see, if you multiply this baby's spectrum with 0, you will get 0, and babies here it is 0. Only if you, because it is 1 here, you are multiplying it 1, you will get only the singer's noise. So this is the major application of this frequency domain analysis. Okay, so you can take only the frequency component which is required. For example, if there is a sound, for example, Marikannu Horimyagi, one song is there in Kannada. So with that, there is a background music, like some rain's sound will be there together. You can eliminate that rain sound or somebody bad singer speaking with the help of this Fourier transform or like Fourier series. Okay, so that is a major application in signal processing, mainly in sound processing, image processing. These are the place where we apply this Fourier series or Fourier transform. I know in mathematics you simply write the equation, you solve that, but what is the application? Where do we use that? How do we analyze that? So that point of view you should get from engineering perspective. Okay, so now if you analyze the signal x of t, it can be periodic in nature. Okay, it will not be periodic in nature also. So if x of t is periodic, then we use Fourier series. Okay, then if it is not periodic, we use Fourier transform. So we convert time domain signal to the frequency domain signal with the help of two things. One is Fourier series for periodic signal. If it is not periodic, we use Fourier transform. Okay, so let me take the practical example so that you will understand where do we use this Fourier transform and why do we need to use this Fourier transform. So you take this specimen image, okay, left side, only concentrate on the first image. So you can see it has a major noise. So what I will do, I will plot them FFT. So in this FFT, there are components which I have marked in red, which is not required. So with the help of filtering techniques, I will remove this. So if I remove this with the help of our filtering techniques, I will get them reconstructed image as shown in figure 3. So this is the important, application. So the Fourier transform allows you to represent an image by its frequency spectrum. And by doing so, we can remove the noise which have a repeating pattern to it. So if you consider this, there are like this noise repeating, this whatever cross marks is there, we can remove it with the help of the filters and we'll get the reconstructed image. So there are many apps in your stores like Insta filters and those kind of things. Okay, so there you can see the old image, if there is any noise or if it is blur, they'll construct in such a way that is the image is good quality. So there and all they will use this Fourier transform or particular type of filters which is related to this frequency domain analysis. So day to day you will use this frequency domain analysis, but you will not be using why, where, what. So this is the basics for that. So I request you to understand the things first, and let us solve some mathematical problems in next class. But we'll understand so why we are reading that chapter, where do we apply, because at the end of the day you are going to become an engineer. So you have to apply whatever you have read in this engineering degree. You have to apply somewhere. So if it doesn't have application, what's the use? So you have read integration, differentiation in your classes, but if you do not use it practically, what is the use? So there is a saying that whatever you study, whatever software you study, finally you have to end up with Excel, Word, PowerPoint, like that. Okay. So yeah, you may say, sir, you are saying so much harikatha, did you apply Fourier transform? Okay. So whatever left side image you can see, that's my image. Okay. So the right image, whatever I have shown you, that's the frequency FFT or the Fourier transform of the image. So yeah, that's the practical application. So image processing is one of the major things. Okay. So coming to the applications, where and all they have used. Okay. First, signal processing. I have showed you image processing, etc. Then in approximation theory, so they will use for this trigonometric polynomial and all. Then control system. There is a subject called control system which you have in XM. So that's very important. So you have to understand this Fourier series, apply there. Okay. For differential equation, difference equation, and they are used to find out the dynamics of the solution there. Okay. So there you will applying, there are many applications. Okay. So whatever applications I have discussed is on the base level. So if you are a programmer and if you want to do something in image processing, you will use most of the time this Fourier transform, this filtering, most of the things you'll use. Okay. For example, as of now there is like computer vision, which is having high salary. So there and all, like you have to extract videos or images, you have to convert into pixels, and then you have to apply signal processing techniques, and then comes your machine learning model things to apply there. Okay. So these are the heavy trend which is going on, which are money making fields. So these are like base things which will help you. Okay. So coming to that, yeah, I've prepared another one here. Okay, let me go to that. 1 minute. Yeah. Okay. So yeah, as of now, we have discussed about practically what is this application and all. Let's go to now to the topic Fourier series. Okay. So who introduced this Fourier series? This guy here, Joseph Fourier. This guy is a great guy because it's another domain, right? So this guy introduced for us the Fourier series. Okay. The Fourier series expansion is used for periodic signal. For aperiodic or non-periodic, we use Fourier transform to expand them in terms of their harmonics, which are sinusoidal and orthogonal to each other. So in the beginning of the class, I asked many people. So you told you are expressing, you are decomposing them signal into sines and cosines. So actually, what do they give? They gives us the analysis. Okay. So for analysis purpose, we use this Fourier transform and Fourier series. Okay. So we have used this Fourier transform and Fourier series for the analysis of the signal. But then you might ask, why do we use this Laplace transform? Why do we use this Z transform? So they are used for design purpose. Okay. So Z transform is used for discrete time signal. Laplace transform is used for continuous time signal. So for the design purpose, we use that, and we use them for the stability. So whether the system is stable or not. So this thing you will read much more in control system about this Laplace transform, stability, Z transform. Z transform you'll learn here, but actual stability or in the system point of view,
whatever I am teaching here is in terms of signal point of view. But if you consider a system point of view, control system is a very important subject again there. Okay. So this things, whatever basics I teach you, will not only helpful for signals and system, but it will be helpful for you for understanding digital signal processing, control system, and other subjects also, because harmonics, everything will come to each other. So let us see what are those things. Okay, what is this periodic? What is this periodic? I have explained to you, but I'll explain again. Then what is this harmonics, and why in terms of sinusoidal, why not other terms? We'll see.
Okay, first we will see Fourier series. Okay, Fourier series is applied to periodic signal. So if Fourier series is applied to continuous time signal, it is called as continuous time Fourier series. Okay, so if Fourier series, if it is applied to periodic signal, it is known as continuous time Fourier series, and you can apply only to this periodic signal. You can't apply to non-periodic. So what is periodic? Which repeats. So you see my drawing there, which repeats continuously. Okay, okay. Now, if you apply for discrete time, then it is discrete time Fourier series. Okay, so Fourier series, whenever I say it is, you have to keep in mind we apply for periodic signal. If it is for continuous time, we are saying it as continuous time Fourier series. If it is for discrete time, we are going to say it as discrete time Fourier series. So in this chapter, in this particular module, we are going to study only about Fourier series. So you have solved many problems with respect to Fourier series in mathematics. The same thing you are going to solve here. And this is like a small module actually. But actually this Fourier transform is a little bit more you will learn there, because properties will be there. Discrete time Fourier transform is there. Fourier transform separately is there. So properties you have to learn. With respect to that, you have to solve the problem. So sampling, everything comes there. So this Fourier series is just like, we can finish it off fast, but this Fourier transform will take time. Okay. So if you consider, real time signal, okay, they are not periodic in nature. Okay. For example, I am singing this song, Ashik Banaya Apne. It's not periodic. It has many frequency component. Okay. So to analyze that one, we use we use Fourier transform. So if Fourier transform we mainly use for non-periodic signals, and if it is used for continuous time signal, it is known as continuous time Fourier transform. If it is used for discrete time signal, it is called as discrete time Fourier transform. Okay. Now, what is this harmonics? I have to explain you. So consider this signal x of t is equal to 2 sine omega t plus 1 sine 2 omega t plus 7 sine 3 omega t. Okay. So this component 1 omega t is nothing but your fundamental frequency. Then you have other frequency, which is the integral multiple of this frequency. For example, you take 2 omega t. How did you get that? Multiplying 2 to this fundamental frequency. So this is nothing but your even harmonic. So what is your odd harmonic? It is this 3 omega t. So this components 2 omega, 3 omega, they are all harmonics. Okay. And what is the fundamental frequency? This 1 omega t in this particular signal. Okay. So if you want to get this square wave, we can decompose this square wave into, we can get this square wave from sinusoids. So you consider this as the first sinusoid, and this blue thing as your second sinusoid, and yellow, green, everything. So if you add all those things, you'll get this square wave. So don't worry if you don't understand this. I'll play an animation video which will give you a better understanding. So how can we obtain a square wave? By adding this sine wave. Or how can we decompose this square wave into this sine and cosines? Okay. So that is nothing but your Fourier series. Okay. So it's just like you're passing this square wave through a prism to get the different components of the signal. What are the different frequency components? So this Fourier series or Fourier transform is just like a prism to you. Okay, so just think of a prism, okay, where a signal passes, and so whenever a light passes, it gives us like seven different colors. Okay, different colors it will give. Same thing, you pass this square signal, you can decompose the square signal into different sinusoids or cosines. That is the main intuition which you have to take from this one. Okay, okay. So now, I think you have understood this frequency domain, but actually, what are you doing in this frequency domain analysis? Okay, so you have this 15 rupees. Okay, my question to you is, how many 5 rupees are there in this 15 rupees? Okay, the answer is, how do you obtain? There are 15 this one rupees, and you divide by this 5 rupees, you will get answer as 3. The same thought process, why can't you apply to the signal? Okay, so our question will be, how much 20 hertz signal is there in a particular signal x of t? So you have your signal x of t. What you have to do to see how much 20 hertz signal is there? Divide by the 20 hertz signal. So whatever you get is the frequency component. So how many frequency 20 hertz component you will get? That is nothing but your Fourier transform, or nothing but your frequency component of the signal. So let me make you understand. Okay, so you have read in Fourier series x of t, this is analysis equation, and another one is synthesis equation. Okay, but what is the physical meaning? Why are you doing that? So x of t is equal to summation k varies from minus infinity to infinity x of k e power j k omega naught t. So this is known as analysis equation for Fourier series. Okay, so in order to get your Fourier coefficient x of k, so where is your frequency lies, this will give x of k. So what do you do? 1 by t integral 0 to t x of t, you multiply by e power minus jk omega naught t dt. So this one you have learnt in maths, but you should have asked yourself, why did I do this? What is this x of k? So x of the k is nothing but your frequency component. So as I told you in the previous example, so we have this 15 rupees there. So how many 5 rupees are there? So I divide by that. So if I want a particular frequency component of a signal like 20 hertz from a signal, I divide by that particular signal. The same logic you are applying here. Okay, it's simple. So you have your signal x of t, and you are dividing by that e power jk omega naught t. Okay, because you want to obtain the frequency component. Okay, and then when it goes up, you multiply that by e power minus jk omega naught t, and then integral 0 to t. Then if you take sum of all the time, you will get your frequency component. So you have to understand the equation. What does that represent? What is its actual physical meaning of that? Without that, if you simply say, I'm doing Fourier series, I'm doing Fourier transform, I'll solve the problems, what is the need for you to become an engineer? Okay, so when you are an engineer, you need to understand the things first. So 1 by t integral 0 to t, so I'm multiplying this x of t by e power minus j k omega naught t. Why did I multiply that? So what it is doing there? So it's giving me the frequency component when it is added over a particular of time. So this signals and system, the beauty is that you can visualize that. Okay, so having said that, so your Fourier transform is nothing but you have the signal here x of t, then you divide by a bunch of sines and cosine, you'll get them Fourier coefficient. So this is real, and you will get the imaginary part. So how do you want to reconstruct the signal? So you have this Fourier coefficients with you, you multiply that because it is ulta, multiply by a bunch of sines and cosines, so you'll get them original signal. Okay, so what we are doing, basically in Fourier series or Fourier transform, you are having a signal. You are multiplying or multiplying by this sines and cosines, bunch of sines and cosine, to obtain the frequency domain component. So if you want to do reverse ulta, you have this frequency domain signal, you multiply with sine and cosine, you will get the original signal. Here multiply because it is reverse, here divide, it is forward part. So this is what you are doing, in frequency domain analysis. This is what you are doing in maths in Fourier series. Okay, so I have explained to you what we are doing, in intuition times. In intuition point of view, let us see a graphical explanation which provides us a good information about this Fourier series. Okay, let me play that to you. Give me a minute. Okay. 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 So we have x-axis and we have y-axis here. So let us create an axis which is giving us an angle theta here. Okay. So the green line rotates by an angle theta. So your x coordinate represents the cosine of the theta. Your y coordinate represents the sine of the theta. So see, how can you see visually this sine wave? Okay. So this angle ranges from minus infinity to plus infinity. So this two dimension, what you can see, this is nothing but your sine wave. So sine wave, you can see visually here. Okay. So I'm changing the amplitude here. Okay. We can also change the phase. So there is some delay. Okay. And also we can change the frequency. So let us consider two sine wave with different amplitude. One is with 3 by 4, which is represented in blue in color, and another one which is represented in red in color with the amplitude of 1 by 4. So how can we add these two? So now we will consider where they have different phases. Phase ka matlab, one is that blue color, let it be sine theta, and red color will be sine of theta minus pi by 3. Okay. How can it be represent graphically? So the frequency will be same and they will have different amplitude and phase when you add this together. So let us consider when we add two sine together, let it have a different frequency. Like, see, there is a delay because it's animation video. You can't play in Google Classroom properly. Okay. See the resultant waveform, whether it's a sine wave, no, it's changing to some other wave when you're adding the sine waves together. So this is the resultant, what you get. So let us consider the point where we add three sine waves, okay? One of sine theta, one of sine 3 theta, and one sine theta with different amplitude and phase, okay? Or we can add another sine waves, like 4 sine waves if we add. There's a delay in animation, okay? Sorry for that. Also, we can add 5 sine waves. So if you go on adding many sine waves, what do you get? Please observe that one. So that's the beauty. So we are getting like a square wave, right? Yes. So by adding infinite number of sine waves, we'll get this something called as square wave. So that's the beauty. You have visualized the things now. So we have got square wave. Let's add like different kind of sine waves. What we will get, we will see. So what you are getting there, a ramp kind of view. Yes, a ramp kind of view you can watch there. So by adding infinite number of sine waves, now we have produced this ramp wave. So what can we get the conclusion from this one? Any wave can be decomposed into sines and cosine. So that is the main intuition we should get from this one. Okay. So this is the practical video which has demonstrated this one. So let's see what does this extra information it gives us. Sorry for that delay in this one. You know, video doesn't play properly in classroom because there is some delay while transmitting. So this amplitudes of each sine wave, you can imagine like a bunch of sheets together. Okay. So as I told you, we can imagine each sine wave or each cos wave as different sheet and different frequency as different thickness or the density of the paper. So when it combines, you'll get a big block. So if you consider when they are closer together, there will be different density for different papers, right? So like that, you can visualize this. Each wave will have different frequency. So it's just a combination of this frequency. Frequency spectrum of a waveform. So analyzing this different frequency is nothing but your frequency spectrum. Okay. So the signals which you see in real time will have a beginning and an end. So you can visualize in terms of combination of infinite number of sine waves, and each sine wave has no beginning or ending. Like that, you can visualize that. So this is the major point which you have to see. All signals we see in real life can be thought of the combination of an infinite number of sine waves that have always been present since the beginning of the time, and which will continue to exist throughout all the eternity. Okay. So that is why we need this Fourier series or Fourier transform. Okay. Okay. By this video, you can refer this video by Eugene, this guy. So it is there in YouTube. Okay. So yeah, since it's time, let's wind up for today. So it was just about the intuition with respect to signals. In the next class, we'll start with the problems with respect to Fourier series, and that module is small. This Fourier series